Hello dear students, today we will study about a very important parameter, density of a material, density of a crystalline material. And in this topic we will derive the relation between the density of a lattice and lattice constant. It is very important as the properties of a material, properties of a lattice strongly depends upon its density. So the precise measurement, precise knowledge of the density of a lattice is very important to us. So mainly two type of structures are there in lattices, that is cubic closed packed and hexagonal closed packed structures. So in the present topic we will deal with both the structures and try to solve numericals related to the topic. So we assume that let capital M be the molecular mass of the given material. So it means what this implies, that m gram of the material that we are dealing with contains Avogadro number of molecules. Avogadro number we designated with capital N. It is 6.023 10 raised to power 23 Avogadro number of molecules. This is a simple mole concept, and in the present scenario we assume let capital N be the number of molecules present per unit cell of the lattice. As we have studied in cubic closed packed structures, the FCC structure, face centered cubic, this value is 4. Hexagonal closed packed structures, for FCC structure small n, here small n is 4, and for HCP structures small n is 6. This we have studied in detail in one of our previous lectures. So we assume let capital V is the volume of the unit cell, so to find density we need mass of atoms or mass of molecules present in a unit cell divide by volume of the unit cell. So volume of the unit cell we assumed it capital V. Now our main aim will be what is the mass of molecules present in the unit cell, and for that we apply a simple unitary method. So let n molecules, n is Avogadro number, n molecules of the material has mass capital M. One molecule of the material has mass m upon capital N. And how many molecules we have in a unit cell? It is small n. So small n molecules which are present in a unit cell, their mass will be m by capital N into small n. So this is our mass of the unit cell. This is this quantity is this one. So if we substitute it, then the density it will be m n upon capital N divided by volume of the unit cell. So this is the formula we will be using in different numericals. And if we assume it is a cubic structure, and that is FCC cubic, face centered cubic, then small n is 4, number of atoms per unit cell, and volume is a cube, where a is the edge length of the cube. Then the density will be m into small n, here we will use 4 upon n a cube. And for HCP structures, small n is 6, and volume, we have derived the formula for volume in the previous article. For a HCP structure, it is 3 root 3 divided by 2 a square c. Here a is the edge length and c is the vertical height of the hexagonal closed pack structure. Then it will be m into small n divided by capital N divided by volume, 3 root 3 divided by 2 a square c. So this is the relation. So these two formulas are very important. Formulas for estimation of density of the lattices in various important structures in which a material undergoes, and they give the estimation of density of the material. So now we will solve the numericals related to these formulas. So the first numerical is copper has FCC structure and its atomic radius is 1.278 angstrom. Calculate its density. Atomic weight of copper is 63.54 gram. Solution. So this is a FCC structure. So here we will apply this formulation for the FCC structure. So as radius, atomic radius is 1.278 angstrom. So for FCC arrangement, A is equal to 4R upon under root 2. This we have derived in our previous lectures. So it is 1.278 angstrom divided by root 2. So edge length for FCC arrangement comes out to be 3.61 angstrom. Number of atoms present per unit cell in FCC arrangement, as we have just studied now, is 4. So the formula for the density is m into n divided by capital N Avogadro number AQ. So mass is 63.54 gram. Number of atoms per unit cell is 4. Avogadro number is 6.023 10 raised to power 23. And as this is in grams, so it should be in centimeters. So it is 3.61 10 raised to power minus 8 centimeter. 3.61 10 raised to power minus 8 cube. So density comes out to be 8.98 gram per centimeter cube. This is in CGS because the whole numerical is solved in CGS. So this is how we deal with the different numericals for cubic structures. So second numerical is for materials having HCP arrangement, second kind of numerical. So zinc has HCP structure, hexagonal closed pack. HCP mean hexagonal closed pack. Height of unit cell for HCP arrangement is 0.494 nanometer. Nearest neighbor distance is 0.27 nanometer. Atomic weight is 65.37 gram. Find the volume and density of unit cell. Find the volume and density of unit cell. So solving this, what we have, height we written by letter C, 494 nanometer. So it is 0.494 10 raised to power minus 9 meter. Nearest neighbor distance is written by letter small a, 0.27 nanometer. It is 0.27 10 raised to power minus 9 meter. Capital M is 65.37 gram, and as it is a HCP arrangement, so number of atoms per unit cell is 6. So firstly we calculate volume of unit cell. Volume of HCP unit cell, it is 3 root 3 divided by 2 a square c. So 3 root 3 divided by 2 a square, 0.27 10 raised to power minus 9 square, 0.494 10 raised to power minus 9. So when we solve it, we get 9.35 10 raised to power minus 29 meter cube. So this is the volume of the unit cell. Firstly we have to calculate this. Now we come to density. Formula for density is m into small n divided by capital N into V. So density of the unit cell is m into small n by capital N into V. M is, here we use SI system, so we convert mass into kilograms. So capital M is 65.37 gram So it is 0.06537 kilogram. 0.06537 kilogram into 6.023 10 raised to power 23. Volume is 9.35 10 raised to power minus 29. And when we solve this, the answer is 68 kg per meter cube. So this is the density. So dear students, these two numericals are very important from exam point of view. So this completes today's lecture. Keep in touch for next lectures. Thanks a lot.